Let me start the recording real quick. So, does anybody have any questions y'all want to go over? Anything? Oh, yeah, that's fine. I didn't finish teaching it, so it's fair. Yeah. Yeah, I got you. Yeah. I always open up like the homework like the day before. So like last night, today's homework opened up kind of thing, you know? So like do it whenever you get a chance, you know? Yeah. Yeah, I got you. I got you. Well, you got time. You got all the way up until like next week. You know, that sounds like a psychologist. I mean, yeah. Yeah. Hi, how are you? Ooh, you wearing my college colors. That's what's up. You know? Yeah. That was a vending machine? Okay, okay. I was about to say, like, yo, they coming up over here, like yo, I went to the library, y'all. They had sushi like crazy over there. I don't know if anybody eats sushi, but yeah, they had sushi and they had like one of those what do they call those? They had salmon today. There was salmon and rice and all that, and yeah, and there's like this Chinese bowl. It looked like a salad, but it has like pasta and shrimp in it and stuff. Yeah, yeah, they had all that in the library. Yeah, yeah. You could go right now if you want. They close at 3. Oh, I got you. Got you. Got you. Got you. Got you. You could come here. I think we're the only ones that use this classroom. So yeah, you could come here and chill if you want. Yeah. Yeah, yeah. I don't think so. That one time that class came in was because they didn't like their classroom, but like I think they found somewhere else. So yeah. Yeah, yeah, yeah. Yeah. Like that's what I used to do when I was a student. Like if the classroom was empty, come up in there, do whatever I want, you know. Back in my day, I used to turn on the projector, watch my movies and stuff like that, everything. Huh? Yeah. Yeah. Yeah, no, nobody bother you. Yeah, they're pretty cool. Yeah. So nobody got questions. Everything is straight. All right. All right, go ahead. 6, okay. Show me that. Yeah, yeah. Yeah. It's fine. Y'all have till like next week, Wednesday, so y'all got time. Yeah. When like all the homework is due. Like everything that's posted. Oh no, yeah. Yeah. Oh yeah, on Monday or Tuesday. No, no, no. That's gonna be for later. Yeah. 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 Mhm. Yeah. All of them. All of them. I owe y'all a video from yesterday. Oh shit. Hold up. I am so sorry. All right, it's gonna take a few minutes to render and all of that, but it's working. Just letting y'all know. All right. Yeah. All right. So I got you. I got you. Let's pick up where we left off last time. All right. So we was doing the histograms. The histograms, right? The drawing with the bars. Remember the bar graph thing at the end? Yeah. Like the frequency distribution and the yeah. So here's where we left off, right? I was drawing it, but I'm gonna use a computer drawing because my handwriting is not so pretty, right? So I was comparing the two different histograms that we have, right? So we have the frequency histogram right here, and we have the relative frequency histogram. I want you to notice that they're the same, right? They like in terms of the way they look, right? They have the same class boundaries, right? And they have the same shape, right? The difference between them is the y-axis, right? For the frequency, you have whole numbers, and for the relative frequency, you have decimals, right? It could be fractions too. Like I leave mine as fractions, me personally. Your choice. All right. It's always a fraction. Yeah, or decimal or fraction. Yeah, yeah, yeah. Yeah. But the shape of it looks the same, right? And if you remember from yesterday, how I manipulated my graph, right, was I just divided all of the whole numbers by the total of everything. So, for example, um, like I had 6 right here, I just put it over 60. 12, I just put it over 60. 18, I put it over 60. 24, I put it over 60, right? And that's how you get the zero point 0.4, the 0.3, 2, and a 1, right? So the same graph, just dividing the y-axis by 60 to make it relative frequency. All right. So let's continue. Each bar is a corresponding relative frequency. Notice that the basic shape of the graphs are the same. The only difference involves a vertical axis. The vertical axis of the histogram shows frequencies, whereas that of the relative frequency histogram shows relative frequencies. All right. So that's the only difference right there. All right. Now let's talk about the shape of the graph. That's another conversation in itself. All right. So coming back, distribution shapes, right? Histograms are valuable and useful tools. If the raw data came from a random sample of population values, the histogram constructed from the sample values should have a distribution shape that is reasonably similar to that of the population. Several terms are commonly used to describe histograms and their associated population distributions. Mound-shaped symmetric. That's the first one we're going to talk about, right? This term refers to a mound-shaped histogram in which both sides are more or less the same with the graph when the graph is folded vertically down the middle, right? And then I'm gonna show you all a picture of that right now. 1 second. Mm-hmm. Yeah. So let's put a picture to that description, right? So when I say mound shaped symmetrical, this is what it looks like. All right. A little bit bigger. So basically, like both ends are kind of the same, right? And it just kind of comes up and then goes down like that. That's mound shaped symmetrical. It can be folded in half, right? Where the left side is equal to the right side, right? That's what they mean by symmetrical, right? That's mound shaped symmetrical. Let's talk about another one. All right.
Oh, wait,
Mm-hmm.
that, right,
Mm-hmm.
this year,
Yeah.
wasn't it like, it was like different parts of it, and it had numbers, it was like 3 point something, or like,
Mm.
I don't remember the number specific. But I
Yeah.
remember it, so it added up to like percentage.
Oh yeah, we're coming to that. Yeah, that's the next test. Yeah. So that's in probability. Yeah, we're not there yet. But yes, they have standard deviations away from each other and all of that. Hmm. So the next one we're going to talk about is called uniform or rectangular. So these terms refers to a histogram in which every class has about equal frequency, right? From one point of view, a uniform distribution is symmetric with the added property that the bars are of the same height. So this is what uniform looks like. They also sometimes call it rectangular, right? So it's just a square. They all have the same height, right? So remember how we had our frequency table? and then we would use the class width to make the bars and stuff like that, the histogram. So these are the different ways that a histogram could come out, right? So you have symmetric, right, where left is equal to the right. This one is called uniform, right? And then I have two more to show y'all. Actually, no. Yeah. This is just like a graphing thing, the way they look.
This is part of statistics, right?
Mhm.
Yeah, 'cause
Yeah.
it's like, honestly, they talk about that.
Right.
It's
Because
crazy.
you see with psychology or every major, right? We collect data, but we don't want to stare at numbers all the time, right? So these are the graphical representations of what the numbers mean, right? And then we can make decisions based off of that. All right. So now we have this one. This is called skewed, right? So you have two of them, skewed left and skewed right, right? So these terms refer to a histogram in which one tail is stretched out longer than the other, right? The direction of skewness is on the side of the longer tail. So if the longer tail is on the left, we say the histogram is skewed left, right? And this figure shows them right here. So let me show you. So this is skewed left, right? Notice that the tail is on the left,
Wait.
right? So there's a tail right here.
So if there's something lower at the end, so
Mhm.
if the, wait,
Yeah.
so if there's something lower than the highest on the left side,
Mhm.
then it's skewed to the left. If there's
Right.
something after the highest bar on the right side, then it's
Skewed
skewed to the
right.
right.
Mm-hmm. Yes, this one would be skewed right. Right. So the tail would be here.
Cause that's the lowest
Mm-hmm.
after the
So
highest.
so think of it like this, right? Imagine you working in a job, right? And then you're looking at everybody's salary that works at that job. Hey, so like imagine that you're looking at like all the workers, let's say all the workers are making like 50, 60,000 a year, but you have the CEO who's making like 1 million a year. You know what I'm saying? So then that would be like a skewed right, because like his salary is so great compared to everybody in general, you know. Skewed left. I'm trying to think of an example right now, but I'm like drawing a blank. But,
I probably said it was, all of these numbers, it was skewed to the left.
right, that's
Is
it.
that kind of like the same concept?
It is the same concept.
So in that particular equation, I will go with the lowest number. So that's
Wherever the tail is, if the tail is on the right, it's skewed right. If the tail is on the left, it's skewed left. You know? Yeah.
Why?
So like I was saying, like let's say we're at your job, right? And we're looking at everybody's salary at your job in general per year. Now, everybody, let's say, is making around $50,000 a year, right? But you got the CEO over here making like 1 million a year, right? So that would be skewed right, because like majority of people's salary is over here, you know. But then you got the CEO and all of that, they down here. They making so much more compared to everybody else. Right. The bar is representing the number of people, not the salary itself. Yeah. Like how many people are making $1 million a year? Huh?
Okay,
Yeah.
I'll leave a little tiny bit.
Okay. Good.
So how would you find the self, like, the numbers with the school to the list?
So that's just adding up all the people in the chart. Yeah, that's all that would be. Yeah. But the x-axis, that would be like the salaries. For example, just throwing out an example. And I can't think of a skewed left example. Like my mind is drawing a blank right now. When like too few people are doing something compared to a majority.
I'm sorry, Teach.
Yeah. And I can't think of a skewed left example right now. I'm like drawing a blank on that. But a salary one for skewed right.
How about like the child's milestone, the average,
Could be.
It's a good one.
Could be. Yeah.
like,
Yeah.
percentile?
That could work. Absolutely could work.
I'll tell you from the range.
True. True. That could work. All right. Here's another kind of graph that we could get, right? We have something called bimodal. So this term refers to a histogram in which the two classes with the largest frequencies are separated by at least one class. The top two frequencies of these classes may have slightly different values. This type of situation sometimes indicates that there are samplings from two different populations, right? So let's take a look at what bimodal looks like. All right. Hold on 1 second. I'm just gotta. So this is what bimodal looks like, kind of, right? I have two peaks, right? Bimodal, right? So there's like a peak right here, and there's another peak right there, etc. Right? So that's bimodal data, right? Now, bim has two peaks, yeah. By two, right? So a bimodal distribution shape might indicate that the data are from two different populations. For instance, a histogram showing the heights of a random sample of adults is likely to be bimodal because populations are male and female where they combined, right? Got you. Got you. I'm sorry. Got you. All right. If there are gaps in the histogram between the bars at either end of the graph, the data might include outliers, right? So an outlier in a data set are data values that are very different from the other measurements in the data set, right? No, 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 like going back to that whole like CEO example, right? So we all over here, we making 60, 70,000 a year, but he making 1 million. So he on his own by himself there. There's a huge gap between what the majority of us is making and this one blesser or whatever. Yeah. All right. It's funny though, because if we like complain and they retaliate, they'll give us the opposite weather, like too much. Yeah. So outliers may indicate data recording errors. Valid outliers may be so unusual that they should be examined separately from the rest of the data. For instance, wow, they took my example. In a study of salaries of employees at one company, the chief CEO's salary may be so high and unique from the company that it should be considered separately from the other salaries. Decisions about outliers that are not recording errors need to be made by people familiar with both the field and the purpose of the study. All right. All right. So something that we didn't talk about yet, but we'll mention it right now. Right. So what do histograms and relative frequency histograms tell us, right? Histograms, right? Huh? Yeah, yeah, right. So histograms and relative frequency histograms, they show us how the data are distributed by looking at such graphs. We can tell if the data distribution is more symmetric, skewed, or bimodal, right? If there are possible outliers, we can see that. Which data intervals contain the most data, we can see that from the picture, and how spread out the data is or are, right? And then in the next chapter, we'll look at measures of center and spread of data. Histograms help us to visualize such measures, right? It'll be there, yeah. But it's gonna be easy though. Yeah,
Yeah, you put 9.
yeah.
How much?
I mean, if you did the homework, you're good for the test. You know, yeah. I mean, all I did was copy and paste it, so I was like, yeah.
You know, spaces. Yeah.
Yeah. Just copy and paste. That's all. Yeah. Thinking about the 18th. Yeah. We'll talk about it next week. We'll talk about it next week. Yeah. Yeah. I'm thinking about the 18th. Yeah. Yeah. I mean, you could think of it as a quiz. Like, I'm just telling you when it is. But do you need it? It's literally the homework. Like, it's literally the homework. Like, I just copy and pasted the homework, and that's it. Not all of it. Not all of it. Like one question. Huh? Yeah. 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 It's more simple than what you think it is. Yeah, it's mad simple. You can use your calculator, you can use the formula sheets. Yeah, I got the formula sheets, you know? Yeah. Huh? Yeah. Yeah. Just like the homework. It's just like the homework. Yeah. Yeah. But you did so much homework that you know how to do it now, right?
Yes.
Yeah.
Damn.
Unless you're telling me I'm not giving you enough homework, you know, like, gosh. But remember, I was telling you could use AI to create other practice problems, right? So like if you want more practice in a particular topic, you know, yeah. I know I was stingy on some of the homework questions. Like some of the statistics stuff had like one question, you know, and that was it. Yeah, yeah, yeah. Those aren't bad. Those aren't bad. We got some more today, actually. Yeah, yeah, yeah. Mhm. Mhm. Yeah.
Okay, this asking us what they are, like in this view for the letter.
Sure, sure. I got you. I got you. Let me just finish this one and then we can do that. Right. So look, cumulative frequency tables and ogives, right? Sometimes we want to study cumulative totals instead of frequencies, right? So cumulative frequencies tell us how many data values are smaller than the upper class boundary, right? Once we have a frequency table, it is fairly straightforward. It is a fairly straightforward matter to add a column of cumulative frequency. So the cumulative frequency for a class is the sum of the frequencies for that class and all previous classes. All right. So remember yesterday how we had like our frequencies? Yeah. Let me grab our frequency. Like this one particular column I'm looking at. Let me just bring that back up real quick. 1 second.
You're my favorite.
Thank you. I mean, you probably like gonna get the highest grade. So look, we got class, we got frequencies. So this is cumulative frequency, right? Let me copy this word. Yeah, this is something new, right? Yeah. The Quency. All right. So cumulative frequency, right? So this is from the table that we did yesterday, right? So the first class that we had, right, had 14. The next class had 21. The next one had 11. The next one had 25, 4, and 4, right? So to do cumulative frequency, sorry, right? You start off with the first class. So this is going to be 14. And then you add the next class to it,
Plus
right?
21.
Right. So 14 plus 21 is what? Uh,
61.
35.
35, right?
No,
Yeah, 35, right? And then now you're going to add the next frequency to that. So 35 plus 11, what's that? 46. That's it. Then you're going to add the next class to that. Sorry. So that's 52, right? And then another class to that, 56. And then what's the last one? 60. And that's the total number of numbers that we had here.
You know what's the
Right.
only thing that's confusing me right now?
Mhm.
The only thing that's confusing me right now is the fact that when you were, okay, so all the way in the beginning, yeah, that part is like super simple.
Yeah.
But if you guys remember, all the way in the beginning,
Mhm.
when you were trying to find something else, you added the last one instead of subtracting it. And I'm still confused about
Because
that.
the next one didn't exist. So that's why I had to add the class width to it.
So it's
Yeah.
not exist, right?
No.
The next one is never gonna exist,
No.
and instead of minusing from one
One.
greatest, we add.
You add the class width to the previous grader one. Yeah.
I want to say,
Yeah.
I was like, why?
Yeah, she
Why did we do
it's
that?
just because we didn't have the next number. Go back up. You want the definition?
Yeah.
Okay. Oh,
Yeah.
okay.
It's just the logic.
I got you. That's why you have formula sheets and you have calculators.
So back at my phone.
You heard yourself on YouTube? Nice.
Like,
You're a celebrity now.
Damn, so everything we say goes on YouTube. I don't know.
Maybe you guys can just sit in the front, but those in the back, you probably can't hear.
So sitting on-
Unless it's really quiet.
Yeah. No, they mean on YouTube. Yeah. You can. Oh.
If you talk loud enough, yeah, it's really good.
Interesting. I didn't even know that. So this is the procedure of how to make an ogive, right? So how to make an ogive. You make a frequency table showing the class boundaries and the cumulative frequencies, which we just did right here. For each class, you make a dot over the upper class boundary at the height of the cumulative class frequency. Right? I'm gonna show you. The coordinates of the dots are the upper class boundary and the cumulative class frequency. Connect these dots with a line segment. By convention, an ogive begins on the horizontal axis at the lower class boundary of the first class.
Is this gonna be, that's horizontal?
Like a graph.
Mhm. It's a graph.
Yeah.
It's a graph.
This,
Right.
this can be an example of like what are the percentile of the kids.
Mm-hmm.
You see a lot of lines,
Yeah. So many milestones.
right?
So let's take a look at an example real quick.
Oh.
All right, so here's an example. So we have the cumulative frequency table in ogive, right? So let's say Aspen, Colorado is a world famous ski resort. If the daily high temperature is above 40 degrees Fahrenheit, the surface of the snow tends to melt. If then it then freezes again at night, this can result in a snow crust that is icy. It also can increase avalanche dangers, right? So this table is going to give you a summary of daily high temperatures in Aspen, right? So we have our class boundaries, which is going from 10.5 to 20.5, etc., going down, right? We have our frequencies already calculated for us. To get the cumulative frequency, right? We start with our first frequency, right? And then we keep adding the next one to it. So 23 plus 43, 66, right? Then we take what we have here, the 43, no, the 51, sorry, and then you add it to the 66, the next one. So on and so forth until you get the total at the bottom. Right. So excuse me, the cumulative frequency for a class is computed by adding the frequency of the class to the frequencies of the previous class, right? As I just showed you in the table. To draw the corresponding ogive, we place a dot at the cumulative frequency 0 on the lower class boundary of the first class. Then we place dots over the upper class boundaries at the height of the cumulative class frequency for the corresponding class. Finally, we connect the dots, right? And then the next figure is going to show you the corresponding ogive. So looking at the ogive, estimate the total number of days with a high temperature lower than or equal to 40. All right, so let's take a look. Let's take a look. Part one or part two? Part one or part two? Yeah.
Wait, you?
No, no. The movie you saw.
Oh, the last.
Accounting too?
No, The Conjuring.
Oh, that's scary. No,
The Conjuring.
I thought y'all talking about the. Nah, listen. All of them was made up except for the first one. That joint was crazy.
City, there's so many started on that.
That joint is scary too.
one.
Yeah. 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 All right, so this right here, this is an ogive. All right. So we have the same boundaries on the bottom on the x-axis, but for the y-axis, we have our cumulative frequencies, right? So, right. Mhm. The boundaries, the class boundaries,
Oh,
right? This thing, right? The boundaries are there. And then the y-axis, the vertical axis is going to be the cumulative frequency, these numbers. Mhm.
upper class boundaries, right?
Right. Mhm.
Okay, so you're
Yeah.
gonna put both of them there.
Right.
Mhm.
Mhm.
Makes
Remember
sense.
that some of the class boundaries overlap, the beginning and end and stuff like that, right? So after that, you put the dots, connect the dots with a straight line. Boom, you have an ogive. Cool, right?
Frequency that you.
Right. Mhm.
After you added
Right.
one to the other.
Exactly. That's it.
Okay, I get it now.
Yeah.
Hopefully I get it when I go home and do it.
That's the question on that, like, what the cumulative frequency, right?
Something like that. I mean, did your homework ask you about it? Did your homework ask you about it?
So,
Sorry, I didn't finish teaching the new homework. But did your homework ask you about this? On web work, did you see questions about this? Just work till you get it, just so you get it all right. So what does an ogive tell us, right? An ogive, also known as a cumulative frequency diagram, tells us how many data are less than the indicated value on the horizontal axis, how slowly or rapidly the data values accumulate over the range of the data, right? So you can look at the slope of it and tell, like, is it getting fast really quickly, or is it like sloping down, or is it dying off? You know? Right. Mhm. In addition, the vertical scale can be changed to cumulative percentages by dividing the cumulative frequency by the total number of data. Then we can tell what percentage of the data are below the value specified on the horizontal axis. Right? Cool, right? Right. So y'all should have enough knowledge now to do yesterday's homework. Mhm. I got you, no worries. I don't even know which one it is, but all right, let's flip the script. All right. Now let's talk about tonight's homework. Radicals. Yay. Y'all probably know how to do this all already. Well, it's okay. All right. So radical expressions. Right. In this section, we will establish some conventions about how we will treat the type of irrational numbers that arise in solving quadratic equations. In particular, we will develop a way of writing square roots symbolically. We already saw in the previous section that solutions to the equation x squared equals a are irrational numbers whenever a is a whole number that is not a perfect square. In this, right, in that decision, we saw that solutions to this simple type of quadratic equation is closely related to the notation of a square root, which we treated in chapter 1 as an operation. One way to treat irrational square roots would be to agree in advance that we will estimate them to a given decimal accuracy. For example, if we agree to estimate square roots to 8 decimal places, a calculator, go ahead. Go ahead. No, go ahead. Go ahead. Go ahead.
No, I just looked at
The decimal.
So,
Yeah, that's a square root. Yeah. So if we agree to estimate square roots to 8 decimal places, a calculator might tell us that the square root of 5, given by square root of 5, for example, is 2.236069798. If, on the other hand, we agree to estimate it to 12 decimal places, we would write square root of 5 is similar to 2.23606797750. You guys can verify that on your calculators, right? So we're going to handle irrational square roots in a different way. Instead of estimating, which depends in practice on using a calculator, we will adopt a symbolic approach, right? So let's take a look at that. It's going to be really fun.
oh,
Mhm.
so in your
Uh-huh. Right? Yeah. That's it. Yeah. It's awesome.
Like,
Mhm. So the square root as a symbol, right? For any non-negative number k, the symbol square root of k, known as the square root of k, represents the non-negative solution to the equation x squared is equal to k. Said another way, the symbol square root of k represents the non-negative number which satisfies the square root of k squared is equal to k, right? That's the radicand, the number that's inside of the radical. Right.
So if it's two, it's two, if it's five, it's five, if it's ten,
Right.
it's ten, that's it.
Right. Mhm. So it is worthwhile pointing out what is new about this definition in our dun, dun, dun.
Inside the game.
When you guys see the actual questions for this, it's going to be like really simple. Yeah, but I just want to explain it real quick. All right. Thank you. Thank you. Mhm. So in our previous understanding of square roots, the square root of k actually consisted of two separate symbols, k representing a number and the radical sign square root, right, which represents an operation performed on the number k. In our new definition, by contrast, the square root of k represents one symbol with two parts, the radical sign and the radicand. Radicand is what's inside of the radical, right? As the quantity k inside the radical sign is known. Keep in mind from the introductory section that the equation x squared equals k typically has two solutions, one positive and one negative. In this case, the square root of k represents the positive solution. From the point of view of solving quadratic equations, at least for simple ones, this definition in a certain sense cheats. We have defined the symbol square root of k to be the non-negative solution of x squared equals k. The other solution will then be its opposite, written as negative square root of k. All right, so the following example is going to illustrate this point. In fact, we can write this as our first strategy to solve a quadratic equation. So first strategy to solve a quadratic equation of the form x squared is equal to k. An equation having the form x squared equals k has two solutions written symbolically as the square root of k and the negative square root of k, the opposite. All right. Whoops. So from now, we will be applying this strategy when k represents a non-negative number, right? In the next session, we will consider what happens when k is negative. Notice that in the special case of x squared is equal to 0, the two solutions, square root of 0 and negative square root of 0, are the same. They are both 0. But rather than thinking of this as a special case of a quadratic equation, with only one solution, it is more convenient to think of this as a quadratic equation with two solutions that just happen to be the same. Okay. All right. Some examples. I got you. Yep. So let's try it. So question one, right? We want to solve these quadratic equations. A is asking us what is x for x squared is equal to 7, right? Real simple how you solve this. Where do I want to do this? I'll do this over here, right? X squared is equal to 7. Let's get rid of that square by square rooting this. But what you do to one side, you do to the other. So what's the answer for x? X is equal to positive square root 7 and negative square root 7. And that's it.
I'm so lost.
You have to write both on the front.
Yeah.
So lost.
So the inverse of an exponent is a root, right? I'm square rooting it to get rid of the square, but what I do to one side, I have to do to the other. But I'm telling you that every time you do the square root of a number, you're getting two answers out, a positive answer and a negative answer. X is square root 7 and negative square root 7.
Okay.
Yeah.
So you.
So how about B?
Two, not positive.
Right. How about B? B is x squared is equal to 129. What do we think? Good. So positive square root 129 and negative square root. Yep, that's it. You just type that in WebWork. Uh-huh. Yeah. Mhm. I'm just hold on. I'm just curious about something. How many times is 3 going to 129? Yeah. What is that? I feel like this is 4. Yeah, 43. And I feel like 43 is prime. So yeah, we're good to go. Good. All right. That's fine. Yeah.
It's not square root of positive 7 or negative 7. We have to actually
It's
solve.
both of them. It's square root 7 and negative square root 7.
But we're not solving.
That is solving it. That's it.
So you don't want us to,
You don't need the decimal. That's it.
so
Yeah.
that's it. That's my answer.
That's it.
7.
That's it. What about C? Do C for me.
Is only positive square root 15.
Yeah.
All right. So square root 15 and negative square root 15. That's right.
That's it.
And to get it, you just square root both sides and that's it. Yeah, that's it. That's all it is. Yeah.
I don't understand why, but okay.
I mean, there is more to it.
Science.
I mean, there's more to it. Like you're raising a whole number to a fraction exponent. That's what it is. So a fraction exponent. Yeah, that's what this is. Yeah. About that. Well, we gotta have a conversation about that.
That's when you gotta multiply. I know you gotta multiply somewhere.
In this?
Exactly. Everything requires a multiplication.
That's a very good point.
You know, so.
Go ahead, go ahead.
Yeah, you know what? I wrote it down, but let me take a picture as well, but I just don't understand.
I mean, yeah, your homework posted if y'all want to try it.
It's just like the other right,
Yeah.
please.
Yeah.
Negative
Mhm.
to the positive.
Yeah.
Alright, so I'm thinking, like, when you first program, I thought it was, alright, so you know how it'll be like, sometimes X is a number, and then they'll have like, it in, putting them something like this, and then you gotta figure out what X is, so, I don't know, I thought that's what you, like, how do you know?
That is what I'm
That's
doing.
that?
That is what I'm doing. I'm figuring out what X is. Both of these answers are X. Yeah.
But, that, alright, so X is 7, not.
X is square root 7 and negative square root 7.
So it's both.
It's both.
Yeah.
Yeah, it's both. Right.
Always.
Yeah.
So you see, x squared equals 129. He did the same thing with the 129. He square rooted x, canceled out the 2, right? Equals, again, what you do to one side, you do to the next. So he also square rooted 129, and the answer is square root of positive 129 is square root of negative 129.
So wait. Here's the reason why. Go ahead.
So long.
Right. Yeah.
That's what she's confusing.
Yeah.
She thinks it's like.
We are solving for X.
No, we are, but the radicals, the other kids.
Yeah. Like when it's a linear equation. I got you. Let me explain though. Okay. Let's say that I have x squared is equal to 16. Right? What two numbers multiply to give me 16? 4 and 4, right? So what I'm trying to do is I'm trying to show you a way to figure this out if you didn't know it was 4.
Yeah.
Right? So I would square root this to get rid of the square. But what I do to one side, I have to do to the other. Right? So that's how I get x is equal to 4. But there's another answer here too. Right? What else can it be? It's not just 4, it's negative 4, right? I want both. I want both. Yeah. Because think about it like this, right? What's 4 times 4? That's 16. But what's negative 4 times negative 4? Positive 16, right? That's the reason why there's 2 answers there. Right? One positive, one negative. I want both answers. Separate them with a comma.
Still want to actually do the square root of 129 and 107.
Right.
And how am I supposed to figure out?
You just solve for X. That's how you solve for X. You undo the square.
What's the square of this, 15?
Square root 15. That's it.
Yeah, like, you can do it like how you did it right. Whatever hands you get, make it a negative.
Negative and a positive.
No, for these.
Yeah.
So
Yeah.
positive 15 and negative 15, but you also want.
Radical expression.
Right, yeah.
Yeah.
So you see, because the first thing is, you see how they act.
I jumped off the cliff,
How they did what?
3 and 5, right?
Okay.
But no.
But when I have it,
No, it's a square root, so it can be.
The way the question is asked to me is, it also should be inside how to solve it.
Exactly.
I know if I'm gonna divide or. Yeah.
And when you're on your test and you forget, it's all on your formula sheet.
15,
I think it's.
Which one's 15?
Because you did the square root of 16, which is, so we
Uh-huh.
got square root positive 16, negative 16, but then we did the answer, which is positive 4, negative 4. Can we still have the 15 as well?
Yeah, we did.
No, we didn't.
We square rooted this, right? Right? To get rid of the square. So now I have x is equal to square root 15 and negative square root 15.
Just like.
That is the answer. That is the answer. Square root 15 and negative square root 15.
16. The answer
For 16, yes. But here's the thing, 16 can get broken down. It's a perfect square, right? 15 is not perfect. Yeah. That's why you just leave it. Yeah. They're irrational. Yeah.
So if it's,
Yeah.
an even number, then we have to further break it down. If it's not. you
If it's a
don't break
perfect
it down.
square,
If
right?
it's a perfect square.
Yeah.
Yeah, that, you see, teacher.
I literally just set it up there. All right.
No, yeah.
It just set it up there.
If the negative sign is in the inside.
We get into that. I didn't get to that yet. But yeah, that there is something about that though. Right?
Take it out.
So if the radicans, right? This is the inside of the radical. That thing, right, is a perfect roots. Then simplify. That's the best way I could put it.
You bring it up.
Yeah.
Make it smaller.
Right.
Smaller to make.
Exactly. Mhm. Yeah.
Like she said, it was inside.
Yeah.
Do it-
Well, when I get some more examples, it'll pop to you.
Do one like she said.
It makes sense.
Yeah, actually.
Now it makes sense.
Do like what?
Feel like you got multiplied.
I feel you.
Nope.
Well, I mean.
It's as simple as this.
The X with the exponent. That's radical.
It's as simple as this.
Is the algebraic expression.
I know that, I'm just saying, the way this, I've had a problem like this.
Oh.
This is only
Yeah.
a portion of it, it's like
Yeah.
one to it.
This, right?
We'll talk about it. We'll talk about it. Was it like in the previous class?
Yeah. Was it this?
Nah.
No.
Nah.
Now, we do that.
I think she's talking about something with variables. All right. Like you had like some letters up in there. A, B. Nah. That's too complicated. We're not doing that. Yeah. Nah, this is all of it. I ain't going further than that. Yeah. Yeah. Nah, there's other there's more to this topic than I'm gonna go. I just want y'all to know how to simplify radicals. That's it. All right. But yes, you can put letters in this and have like 15a squared, and then you're gonna do the square root of, like that's a thing, but we're not going that deep. All right. So the point of these simple examples is not really to show how to solve a quadratic equation, although we have technically done so. The point is to illustrate the fact that we use a symbol to represent a solution to an equation. It has the advantage of needing no estimation. For example, the square root of 129 is a symbol representing the exact value of the positive solution to x squared is equal to 129. It has a disadvantage, however, of hiding the fact that this symbol, square root 129, is a symbol for an actual irrational number whose value is approximately 11.3578166916005472221. Cool, whatever. Right? No, I don't want that. No, I don't want that. You need a whole computer to give you something like that. All right. So there is another more serious disadvantage to this symbolic approach. If we get too excited about this new notation, we would be tempted to say that the solution to the quadratic equation x squared is equal to 9 is square root 9 and negative square root 9 and done. But it's not. This seems like a wrong way to answer the question when it is much more easy to and easily understood to say that the solutions are 3 and negative 3. Because remember, 9 is a perfect square, so it's going to get broken down to 3 and negative 3. So unlike the examples above, 9 is a perfect square, and so there is no need to have a special notation made specifically to address irrational numbers in that scenario. All right.
You want to break it down?
Yeah, it's just 3 and negative 3. That's it. So for these and other related reasons, we are going to agree to a series of rules about how to write square roots symbolically. These rules have evolved over the course of history and are generally accepted. All right, so let's talk about it real quick. You're welcome.
I do. So wait, we only negative and positive things if we like.
And you call it a day. That's it.
was that whole number. Exactly.
If it wasn't a perfect square.
That's,
Yeah. Yeah.
that's what I was going to.
With the 15 one. Yeah.
All right. So simplified square root notation. So the symbol square root of k is called simplified if the following conditions hold. The radicand k has no perfect square factors. The radicand k contains no fractions, And in addition, any expression containing radicals must simplify a third condition, right? No radical expression shall appear in a denominator,
They can appear in
right?
the,
Yes.
oh, hell
Yeah.
no.
So it's illegal to take the square root of a number in the denominator, right? Yeah. Yeah. There's some rules with that. When you guys switch your major to math though, and y'all take math 30, I'll explain that more. You know? Yeah. Yeah.
I don't think so.
Yeah.
We love you, but we don't love math.
Right.
I mean, consider it. You know, it's a dope major. You know. I gotcha. So, what happens if we encounter a radical expression which is not simplified? We will take the effort to simplify it, rewrite it in an equivalent form, which is simplified according to the conditions above. In order to do this, we will rely on two basic properties of square roots. So, here we go. It's about to get fun right now.
Oh, you.
No, this is really cool. This is really cool.
Let's see.
But somebody that shall remain nameless wanted to do multiplication, so I got them. All right, so some properties of square roots, right? If A and B represent non-negative numbers, then the square root of A times B is equal to the square root of A times square root of B. And if I have the square root of A over B, that's going to be equal to the square root of A over the square root of B, and vice versa. Mhm. Mhm. So if the radicand on the inside is, if there's two numbers being multiplied together to get it, I can break them apart separately.
Like how it is right now?
Yeah. Yeah. And if I'm dividing, like say I have a square root of a fraction, I could just take the square root of the numerator and the square root of the denominator individually. Hmm? And don't worry, when you forget it on test day, it's on your formula sheet. Right? Everything. 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 Ah, print it. Print it. Yeah. It's all right. It's open every day, and it's open on Saturday, and I think it's open on Sundays. Don't quote me on that, I don't remember. All right. These properties are really just versions of the properties of exponents we discussed last chapter. For example, the first property really says that the number represented by the square root of A and the square root of B should be the non-negative solution to x squared equals A times B. Is this true? Since the square root of A squared is equal to A and the square root of B squared is equal to B, then the square root of A times the square root of B squared should be equal to the square root of A squared times the square root of B squared, which is equal to AB. I got you. By property E4 of exponents. So the square root of A times square root of B really is a solution to x squared is equal to A times B. And the equality of property S1 is valid. We now show through a series of examples how these properties can help us simplify square roots. So let's take a look at some examples. It'll pop then, guaranteed. Mhm. Mhm. Kind of. Like basically, I'm just going to show y'all how to simplify radicals. Keep it simple, right?
Is this a must?
Yeah. Yeah.
Is that yes?
So look, I have square root of 12. Real simple, right? No, not 6. So here's how you do this, right? You have square root 12, right? You want to find the largest perfect square that goes into 12. What's the largest perfect square that goes into 12? 4, right? So I could break down square root 12 into what? Square root 4 times square root 3, right? Now, what's the square root of 4 again? 2, right? So this is my answer, 2 square root 3.
Oh, cause you gotta keep breaking it down and whichever can, and then you bring it
Right.
back.
Oh, you
Mhm.
I got it.
Yeah. Right. Mhm. So square root 12, like if I write it horizontally, square root 12 is the same thing as square root 4 times 3, which becomes square root 4 times square root 3, which then becomes 2 square root 3. However, which way you like to do it.
Square 12
Mhm.
is equal to 4 times 3.
Square root of 4 times 3.
Cause you need 4 times 3 is 12, breaking it down.
Yeah.
Okay, so the 4 times 3 is in the square root because you broke
Because
down
the 12 is
four
in the
to
square
two
root.
and 3 to 3.
Right. Or the 3 just stay the same, but yeah. Yeah.
Break it down.
Mhm.
This one has to.
Exactly.
I need a perfect square to go into 12. Other numbers goes into, I could have said 6 and 2, but the thing is that 6 and 2 are not perfect squares. I need a perfect square. So only 4 would be the one to go in. All right. Let's try the next one. How about 72? So I have square root 72. Give me 2.
Eight.
What is it?
8 times.
8 times what? I need a
The thing like this, 72. Fine, 8 times 9.
It is, right?
8 times 9. Yeah. So this would become square root 9 times 8, which we could break down into square root 9 times square root 8. And the square root of 9 is
3. Square root.
so 3 square root 8. That's my answer. Done.
Oh,
That's it.
Yeah, 8.
Mhm. Not bad, right?
You see why you would break down the 8 into a 4 or 2?
I'm so fucking wrong.
Why you leave it like that?
You're right. I'm supposed to do that. That's okay. You're gonna go far in nursing. You know that? All right.
Negative, I mean, square root of 3 is the next square root of 4.
How did you find?
You're right about that.
So,
Well, they told me the square root of 9 was 3, so that's why.
Yeah.
Right. But you're right. Square root of 8 could get broken down into square root 4 times square root 2. And then the square root of 4 is what again?
2.
2, right? So this becomes 3 times 2. No, break it down further.
So that's the
Right.
answer, square root 2.
No, this is the answer. 6 square root 2. That's the final answer.
Teach you.
So okay. Let's say we wanted to do this a different way, right? Wait, let's take a look at this another way, right? The largest perfect square that goes into 72 is actually 36, right? So this becomes square root 36 times 2, which becomes square root 36 times square root 2. And then square root of 36 is 6 square root 2.
Because 36 times 2 is 72.
Right.
Oh, and then that.
But it's okay if you can't see the large perfect square that goes in. You're allowed to use smaller square roots to break it down further until you can't anymore.
Hold on, so the square root of 2 is 2?
It's just square roots. You can't, it's irrational. It can't get broken down anymore.
Oh.
Yeah.
Like, make sure.
It's perfect.
Why? I need to know where does, how do I know? Okay.
This is square root 4 times square root 2.
Oh,
You're missing square root 2 there.
because it keeps going.
Yeah. Mhm. All right, let's try the next one. I need another color. How about orange? All right. So square root of 75. Give me the largest perfect square that goes into 75. Yes, you do. Come on, you're a New Yorker. 5? No, give me something better. 25.
Yeah.
Right? So square root 25 times 3. And then that becomes what? Square root 25 times square root 3. And what's the square root of 25 again? I forgot it. So this is 5 square root 3. That's the answer. We're done. All right.
So the 5 goes on the outside, the 3 goes on the inside.
So you found the perfect square.
The
that you can,
Yes. That's it.
but I'm saying, you finding what goes into 25, but where are you putting the three, like, are you keeping?
The three stays under the radical. Yeah. Mhm. You simplify it, all right? You find the largest perfect square that goes in. You simplify that down, you should get some whole number on the outside. And whatever can't get broken down, you leave it under the radical, and that's it.
Leave it as a radical, that's which is the three.
Yeah.
5 is the last one.
5 is the square root of 25.
Remainder. Not the remainder.
No, but that's.
So when I say square root 25, I'm asking you, what number multiplied by itself gives me 25? So, yeah. Mhm.
That's what I was trying to, that's what I was thinking, but you clarified it, like, I
Yeah,
was
she- And that's all it is.
the thing that was that, that's true, right?
Mm-hmm.
That's the lowest one.
Well,
The lowest.
36 is what goes in. And then the square root of 36 is 6. Yep, that is the homework. Yeah. Right. Yeah. Can I borrow a piece of paper from somebody, please, for attendance or anything? Please. Anything, I don't care. What do I want to do?
I see, you know, that's going to be, yeah. Yeah, makes sense.
It's whatever. All right, y'all. Just give me 2 more examples, and then y'all will have all the information y'all need to do y'all homework. All right. Just give me 2 more examples.
What's your last name, Negron? Huh? Susie? Oh.
It's all right. Watch your recording. It's all right. Watch your recording. I got you.
I give it to you.
I just got 2 more examples, and then y'all be good to go for your homework real quick, right? That's good.
Breaking it down, I was like, oh.
That's good.
I like this, this is.
So wait, look at this example real quick. Let's look at A, right? I got square root 3 over 4, right? You can actually break this down and put the square root over the numerator and denominator individually. So this becomes square root of 3 over square root of 4.
And then you divide that.
Well, not divide yet. What's the square root of 4? What's
2.
that? 2, right? So this is my answer, square root 3 over 2, and I'm done. That's it. Right?
You can't do it.
Right. I can't do it anymore. Right?
Okay.
So then let's look at B. Go ahead. What was the question? How's what? How do I get what? Right. So the rule is, right, because they're under the same radical, I can do the radical to the numerator by itself and the radical to the denominator by itself. Right?
You will never have to divide.
No.
That's
Unless
the trick
unless
here.
possible. Unless possible.
Like if it's even.
Yeah.
Then you can.
Yeah,
So it was like 4 and 8.
Right. Yeah. Then you can divide that. But these can't be divided. Yeah. So look, last one. I got square root of 50 over 9, right? Because they're under the same radical,
25.
I can get square root 50 individually and square root 9. Right? Let's keep going, right? Largest perfect square that goes into 50 is what?
25.
25. So this is square root
With your
25 times square root 2 over square root 9. And what's the square root of 25? 5. So this is 5 square root 2 over what's the square root of 9?
3.
3. This is my answer. I'm done.
Oh, I love this.
Right? That's it. Yep. Yeah.
Yeah, but I gotta do the.
I don't have a pen. Yeah. Can I borrow your pen? Can I borrow your pen real quick so you can sign? You're welcome. You're welcome. Oh, good.
Okay.
Good. Yeah. All right. See y'all.
Yeah, nice to see.
Um, one more, I have one more example. I have two more examples, then I'm done. Two more examples.
Obviously, you finish the first set of painting and set, and then I
Nice.
see the other one. I'm like, oh my god, every time
Got you. I got you. I got you. This is the end of it though. This is the end of it. I got you. So give me like two more examples and I'm done. Just two more quick examples. Yeah. 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 I can. I just care that you get 100 at the end. That's all I care about.
Yeah.
Yeah.
No,
So, so look real quick. In the previous example, we were lucky to encounter fractions in the radicand whose denominators were perfect squares. The next example illustrates how to simplify when this is not the case. It involves a technique known as rationalizing the denominator. So here, the word rationalize implies making an irrational number rational by multiplying it by the appropriate number. So let's check this out. Let's check this out. So I'm going to do A real quick, right? We already know this is square root 1 over 2. We can put the radical over the top and the bottom. So this becomes what? Square root 1 over square root 2. Just like that. The square root of 1 is 1. So this is 1 over square root 2. Now I'm telling you, it's illegal for us to divide by a square root. So we have to rationalize the denominator. So to rationalize the denominator, you multiply it by the same denominator. But you got to be fair. What you do to the bottom, you got to do to the top, right? Then you multiply straight across. 1 times radical 2 is just radical 2. And then radical 2 times radical 2 is going to become radical 4, which is just 2. And this is my answer. That's it, right? Let's try B. Let's try B. So for B, I have square root 3 over 8, just like that, right? This is going to become what? Square root 3 over square root 8. I can break down square root 8 to become what? This becomes square root 4 times square root 2. And the square root of 4 we know is 2, right? So this is square root 3 over 2 square root 2. It's illegal for me to have radicals in my denominator, so I have to rationalize the denominator. So to rationalize the denominator, I multiply it by itself. So this is going to be times square root 2. But, I got to be fair, right? Do to the bottom, I got to do to the top, right? So on top, square root 3 times square root 2 becomes what? Square root, no, 6, right? So this is square root 6 over, I already have the big 2 in the front. That's this one right here, right? And square root 2 times square root 2 is going to be 2 again. And 2 times 2 is, right? So final answer is going to be, hold on. It's going to be square root 6 over 4. And that's it. Right? Last example. Last example. And then we good. And then we good. And then we good. All right. Even though we kind of spoke about this already, I want to just do these two examples just to solidify it, and then we can call it at that for today. You're welcome.
now I kind of little bit understand it.
And your homework is already posted, so you guys can practice this, right? So in the challenge exercise in this section, we'll come back to whatever. So we close the section by incorporating our practice of simplifying radical expressions into solving quadratic equations. Here's an example, right? Let's say I have x squared is equal to 16. I accidentally did this earlier, right? So tell me how to do this. I have x squared is equal to 16. What do I do? I'm going to square root, right? Both sides, right? So this becomes So what's the answer? X equals negative,
16
no,
squared.
negative. What's the square root of 16? 4, negative 4, and positive 4. That's it. Right? All right, B is a little bit more complicated. Let's talk about B. I have x squared is equal to 98. I'm going to do the same process I did before. I'm going to square root this side to get rid of the square. But what I do to one side, I have to do to the other. What happens when I do that? This is going to become x is equal to, right? Now, I'm just going to put a plus or minus because there's two answers there, a positive and a negative. Square root of 98 can get broken down into what? Square root 49 times square root 2. And the square root of 49 is what? 7. So this is equal to plus or minus 7 square root 2. Or you could say x equals 7 square root 2 and x equals negative 7 square root 2. Whatever floats your boat. And that's it. All right. Now you have enough knowledge to do your homework for tonight. All right. All three problems of it. All right.
Thank you, Professor.
You're welcome. You're welcome. All right.